What I would like to do today is talk about absorption. In the previous lecture, we looked at adsorption. So when we look at adsorption, we talked about the attachment of molecules onto a solid surface, and that solid surface can be anything from curtains, upholstery, just fabrics, can be activated carbon, as we've talked about, can be various different synthetic materials. So we're looking at typically removing a chemical from the gas phase or the aqueous phase onto a solid surface. Absorption is different. Absorption is, think of it as a three-dimensional process in which we're looking at transferring a chemical from either a gas into a liquid or from a liquid into a gas. So we've talked about aeration systems, and we've mentioned the oxidation of iron. So Fe2+, which is the most common form of iron in groundwater systems, can be oxidized by oxygen to Fe3+, and what happens then is that Fe2+ is oxidized to Fe3+, something has to be reduced, and what is reduced is the oxygen. And in order to balance this equation, we have to balance both electrons and elements. So balance all the electrons, balance the elements, we have this balanced reaction, and it's the oxygen is reduced from charge of 0 to a charge of 2-. We've also talked about aeration systems for wastewater treatment. So we talked about using aeration in activated sludge. Typically, we're looking at diffused aeration. So we have some sort of diffusers, and we're injecting oxygen into that suspension of microorganisms and our wastewater. We also need to aerate in trickling filters. Now there we're looking at more passive transfer. So we're looking at, again, transfer of oxygen from the air into the aqueous phase, and the same is true for rotating biological contactors. In order to disinfect, often we use chlorine gas. That chlorine gas, we add it to water. We're looking at dissolving that gas into the aqueous phase. Okay. We also talked about recarbonation, and there we're looking at adding CO2 to the water, dissolving it in the water. So you have CO2 aqueous, which we talked about forming carbonic acid, so we can lower the pH. So in all of those systems, we're transferring the chemical from the gas phase to the liquid phase. Now, we can also talk about transferring chemicals from the liquid phase to the gas phase. So for instance, where we have groundwater contamination with, for instance, trichloroethylene, we have TCE. Now we start with TCE in the aqueous phase, and we're looking at TCE, or transferring that TCE to the gas phase. Now, why would we want to do that? Well, because in some cases, it's more efficient to treat the chemical in the gas phase. So for instance, we can use catalytic oxidation to treat the TCE in the gas phase. We can also do the same in the aqueous phase, but it tends to be more efficient in the gas phase. Okay. We also talked about stripping CO2 from groundwater. If you remember, reaction 1 was the neutralization of CO2, because we talked about how if we have a significant concentration of CO2 in the groundwater, that increases the amount of quicklime that we need to add and also increases the amount of sludge that we produce. So it's costing us both in chemicals that we're adding and in sludge that we're producing and then have to dispose. So again, now we're looking at the opposite here. Okay, we're looking at CO2 in the aqueous phase, and we want to transfer that to the gas phase. Okay. We can also look at CO2 capture from a combustion stream, so gas stream, and we can look at capturing that into a liquid. So to get that back to that gas to a liquid. All of these processes can be modeled using what we refer to as two-film theory. We have a gas film and we also have a liquid film, the liquid film being significantly thicker than the gas film. So shown here is with, for instance, removing SO2 from a combustion stream. So we're looking at dissolving that CO2 into water, produces sulfurous acid, which we then can neutralize. But in order for this to occur, we need to have transfer. So in order to think of this, okay, the smaller the bubbles that we have, so, or droplets of water, so really the smaller the droplets of water, the greater the rate of mass transfer. Why? So the smaller the droplets of water, we're looking at transferring SO2, in this case, from a gas stream to an aqueous stream. The smaller the droplets of water, the greater the mass transfer. Why? Exactly, more surface area. Exactly right. So one of the things we're looking at in doing here is creating surface area. So in order for efficiency, we need to create that surface area. We also need to mix, and we need to know which of these films, the gas film or the liquid film, tends to be rate limiting. So in order to have transfer, the chemical, so in this case, we'll stick with SO2, needs to diffuse from the gas, the bulk gas, to this interface, has to transfer across the interface, and then has to diffuse away from the interface into the bulk liquid. All of the designs that we look at are based on Fick's law, which I'll explain in a bit, and Henry's law. So Henry's law simply states that the concentration of a chemical in the liquid phase is equal to some partitioning constant, or Henry's constant, times the partial pressure in the gas. So for instance, we can write that the concentration of CO2 in the aqueous phase is equal to Henry's constant times the partial pressure of CO2. And the same holds true for oxygen, trichloroethylene, SO2, etc. So in all cases, we're looking at this equilibrium. So we can think of this as, or we can model this transfer based on this two-film theory. So think of this as this first situation where we have the concentration of a chemical, and let's think of oxygen, relatively low temperatures, the saturation concentration of oxygen in water is about 10 milligrams per liter. The concentration, we'll say, at this point is 2 milligrams per liter. Okay. So in that case, the net transfer is going to be from the gas to the liquid. Why? Because we haven't reached saturation. Okay. On the other hand, if we have the opposite situation, the saturation concentration, let's just keep it at 10 milligrams per liter, but the concentration is, let's say, 12 milligrams per liter. So perhaps in a situation where we have a significant amount of algae in the water, that algae is photosynthesizing, producing oxygen, and now the transfer is in the opposite direction from the water to the gas phase. So you can think of that in terms of the pop can. You open a can of pop, and what happens? CO2 is released. Why is the CO2 released? Pressure. It's pressure differential. Okay. So what happens is the can is under pressure. So because it's under pressure, the saturation concentration of CO2 is significantly greater than what it would be at atmospheric pressure. So it's essentially the CO2 is trapped in the can. So when you release that pressure, what happens? Now, all of a sudden, the saturation concentration decreases significantly, and the CO2 is released as bubbles. Fick's law states that the change in concentration with respect to time is equal to this mass transfer coefficient times the difference between the saturation concentration and the concentration at any time t, which means that if we look at the concentration as a function of time, the rate of change in this concentration, rate of change, will decrease as it approaches the saturation concentration. So the closer we get to the saturation concentration, the harder it is to get more of that gas into solution. And my husband's been in the lab trying to calibrate. He's building a system to test CO2 sensors, but has to calibrate the relative humidity sensors. So he actually has to do this. And what he's doing is calibrating it by using saturated solutions of different salts to create the relative humidity. Well, guess what? It's a really long process. Relatively rapid initially, because that mass transfer rate is relatively high. But the closer you get to equilibrium or to saturation, the slower the process. So if we were joking yesterday, if only Fick hadn't created this law, things would move faster. It's really a model. So think of it more really as a mathematical model. For very soluble gases, such as ammonia, the principal resistance is in the gas phase, which means that we want to make that gas film as thin as possible. Mixing the liquid film isn't going to change things a whole lot because in mixing the bulk liquid in order to reduce the liquid film isn't going to change things a whole lot. On the other hand, relatively insoluble gases, and oxygen is a relatively insoluble gas, the resistance is predominantly in the liquid film. So therefore, mixing the liquid in order to reduce the liquid film thickness actually is beneficial. So understanding how, or understanding the influence of solubility plays a significant role. Okay. The other thing to recognize is that these mass transfer coefficients, typically for a particular unit, for a diffuser, for a mechanical aerator, are provided by the manufacturer. Now, the manufacturer doesn't want to test these in wastewater, so they're tested in clean water. But we need to adjust the values in order to be able to use them for a wastewater or a natural water system. So alpha relates to the KLA, and these vary from about 0.2 to about 0.75. So that means that the mass transfer efficiency in a wastewater is going to be significantly less than what is predicted based on the manufacturer's specifications determined with clean water. Beta relates to the solubility, and the solubility will typically decrease in your natural water or in your wastewater, and this beta values range from about 0.7 to about 0.98, and for wastewater it's about 0.95. Now, the higher the concentration of dissolved solids, the greater the value of B. Okay, so B increases as the total dissolved solids increase. So we can do an example here where we have a mechanical surface aerator, and we're using this to aerate a facultative lagoon. The mass transfer coefficient, KLA, obtained from the manufacturer is 1.05 inverse hours. The water temperature is 15 degrees C, and the values for alpha and beta are 0.85 for alpha and 0.95 for beta. The aerator's been turned off for maintenance, and you're told that when it's turned on, the initial concentration in the water, so C naught is equal to 3.5 milligrams per liter. And we're back to these stupid lines. Okay. And you're asked, how long will it take for the dissolved oxidation concentration to reach 7.5 milligrams per liter? So KLA in the pond is equal to alpha times KLA in pure water, and that is 0.85 times 1.05 inverse hours, or 0.8925 inverse hours. And CSAT in the pond is equal to 0.95 times, now we need the CSAT at 15 degrees C, and that is 10.15 milligrams per liter, and that is equal to 9.64 milligrams per liter. Okay. So ln Csat minus Ct over Cs minus C naught. So it's just the integration of the derivative that I gave you before is equal to minus KLA times T. So if we substitute here ln of 9.64 minus 7.5 over 9.64 minus 3.5 equals minus 0.8925 inverse hours times T. T is equal to 1.2 hours. If, on the other hand, the temperature had been, if the temperature had been 25 degrees C, then our Csat in the pond would be 8.38, and the time would be 2.5 hours. So you can see here in this case, there's a significant decrease in these differences, and the time increases significantly. So the closer we get to saturation, the greater the time. Okay, so I didn't see Obaday's question about is it possible to oversaturate? Yes. Okay, so back to the can. Okay, we wrote that Csat is equal to KH times PCO2. Okay. As we increase pressure, we increase the saturation. So if we increase the pressure in the can, we increase the saturation concentration of CO2. But then when we open the can, what do? We decrease the pressure. So when we decrease the pressure, now all of a sudden the saturation value concentration decreases significantly, and we form the bubbles that we want in soda pop.
Based on this lecture, you should be able to explain the process of adsorption. Also, you should be able to explain Fick's law and predict the concentration of dissolved oxygen or other gases in solution as a function of time and their mass transfer coefficient.